10.5 is a section that talks about computation with series and applications. So we look at an alternating series. An alternating series is a series that switches signs from one term to the next. That's always the case. We haven't played with those yet. And what you need to know about this series, unlike the other series, if you take the limit as n approaches infinity of a sub n, and you get it to be 0, that series converge. Now we're not going to prove whether it converge or diverge, we're just going to use it for what we need. The error, which is something we have to find, made by adding the first n terms of a convergent alternating series is given by the next term. Remember, n terms will be a sub 1 plus a sub 2 plus a sub 3 plus a sub n, and the next term will be the biggest error provided the series is alternating. That's not true for other series, only for alternating series. So we're picking very specific series here. And directions is straightforward. Find the indicated value by means of Maclaurin series, meaning use those tables, using the number of terms indicated. So each of these problems says how many terms to use. Find the maximum possible error and determine the accuracy of the result. So this is sort of how we program computers or machinery. So we know e to the x is 1 plus x squared over 2 factorial. So when I say what is e to the negative 0.3, that is 1 plus a negative 0.3 plus a negative 0.3 squared over 2 factorial plus a negative 0.3 cubed over 3 factorial plus a negative 0.3 to the fourth over 4 factorial. That's 1, 2, 3, 4, 5, 6 terms. One more. A negative 0.3 to the fifth over 5 factorial. Remember, the error will be the next term. If we stop at the fifth term, then we know the error is going to be negative 0.3 to the 6 over 6 factorial. Now, if I work this out, if I put this in my calculator, and that's something you're going to have to work with, that turns out to be 0.713817125. If I figure out the error, this number, the error turns out to be a 0.1234518113. So, and this error is positive. So if I take this number, which is my answer, my approximation, I want to know how accurate is it. If I add 0.00345 to 1813, if I add those, I'll notice that the number so this tells me where to look. This tells me the cutoff is after the fifth decimal. This is the number I'm trying to figure out. So when I want to give this number, I want to know how accurate is it. If I am to stop right here, I want to know if this number is affected or not. If I take the actual calculation and I round, since this is a 7 and I'm going to stop there, wouldn't you say that's 0.71382? And if I take the number with the error, that's 0.7138. Since this is an 8, this will bound to 2. So this is the number I could trust out of this, rounded. So my maximum error is right there. And the number that I can get out of this, it's accurate to 5 decimal places. Beyond 5 decimal places, that 7, that 1, that 2, and that 5, I'm uncertain about. And that's pretty much what you have to do. if I look at the next problem, keep in mind trig works with radians. So when I see 12 degrees, I need to really take 12 degrees and convert it to radians. That's pi over 180 degrees. And that turns out to be pi divided by 15. So I'm looking at the cosine of pi over 15. This is an irrational number. I only need 3 terms, so I only need those 3 terms. I'm going to say that's 1 minus pi over 15 squared over 2 factorial plus pi over 15 raised to the 4th over 4 factorial. And I know my error is actually that term. It's negative pi over 15 to the 6 over 6 factorial, which in turn turns out to be a negative 6 zeros. 1, 2, 3, 4, 5, 6, 1, 1, 7. This summation right here, if I put this in my calculator, that's 0.9781477718. Now, if I take my error and subtract, and we said we had 6 zeros, 1, 2, 3, 4, 5, 6, 1, 1, 7. If I subtract those, I'll get a 0.978147601. So this is the answer, but I need to know how accurate is this. And again, the 6 decimals tell you where to look, exactly where to look. So I'm trying to figure out how accurate is this. If I look at the top green number, if I was to stop here, since this is a 7, wouldn't you round this to an 8? Wouldn't you say the answer is 0.978148? All what you have to do is make sure that this number agrees. If I round this, that does round up. So we will say this is our accuracy rounded. The next problem up, natural log of 1.2. Well, that's natural log of 1 plus 0.2. So that's going to be 0.2 minus 0.2 squared over 2 plus 0.3 cubed over 3. We're going to say that's what the sum is. And if I put that in my calculator, that would turn out to be a 0.18133333 all threes. If I get my error, which is the next term, my maximum error will turn out to be a negative 0.2 to the 4th over 4 factorial. So this is telling me if you decided to only use those 3 terms to describe a natural log, then the error in your approximation is a negative 0.1234. Now, if I subtract a 0.4 decimals, 1, 2, 3, 4, 6, 6, 6, 6, 6, all the way. You do this in a calculator, that turns out to be a 0.18131812. Because this 6 is going to become 7, and then a bunch of 7s after that. 6, let me see, that's 13, no, that's going to be 6. If you notice, the last number would be a 7, so those are going to be all 6s, because you're going to borrow 1, make that a 13, that is a 2 becomes a 12, 2, 2, and so on. So again, the key is for you to figure out this number. Now, if I was to stop here, wouldn't my answer be 0.1813? And if I look at this figure, since I'm going to stop here, by rounding up, that matches. If it doesn't match, I'll go to the lower number, so that number will not be trusted. In this case, this says it might affect the 4 decimals. Well, it does, but with the rounded, it turns out to be okay. So if you use only 3 terms, whatever you get out of that series is accurate only to 4 decimal places, and that depends on what you want to do. I messed up. That shouldn't be a 4 factorial. I just noticed that's a 4. And if I take that into account, so if I take 0.2 raised to the 4th divided by 4, I will get I will get a 0.123 and a 4 negative. So here that will change slightly. And let's see how does that work. It's a good thing that we caught this. So this is 0.123 and a 4. That's it. So if I subtract those, you'll notice that I'm subtracting that right now. That's going to be a 0.1809. Let me put in order. 18. So here this is out of 13. That's a 0, and the rest is all these. So here I would notice that the original runs 0.81333. The approximate 0. So what changed? I notice this number is no longer accepted. So I would say it's 0.18 for sure. Since I know that's the cutoff, I'm looking at this number. If I round this, that's a 1. If I round this, that's a 1. So anytime you round, you will have to say rounded. And that is the maximum error, and that's pretty much it. If I look at example 2, evaluate the integral correct to 5 decimal places. Well, here we're kind of trying to figure out how that works. Well, the series for cosine of x is right there. So this is 1 minus x squared over 2 factorial plus, and I'm just copying what that says. That's infinite. Minus 1, all divided by x squared. Well, this one and that one cancel out. And if I divide those, I'll get negative 1 over 2 factorial plus x squared over 4 factorial minus x to the 4 over 6 factorial plus x to the 6 over 8 factorial, and the list goes on. Now, I'm integrating this from 0 to 1, and that turns out to be negative 1 over 2 factorial x plus x cubed over 3 times 4 factorial minus x to the 5 over 5 times 6 factorial plus x to the 7 over 7 times 8 factorial evaluated from 0 to 1. If you put the 1 in, you will get a negative 1 over 2 factorial plus 1 over 3 times 4 factorial minus 1 over 5 times 6 factorial plus 1 over 7 times 8 factorial, and the list goes on. And if you put a 0, you get a 0. So now I'm trying to figure out how does this work. So what I do, I pick a number, let's say that number, and I figure out what that equals. That turns out to be 0.000277 all the way up. So I know this affects the 3rd decimal place. I need it accurate to 5 decimal places. So obviously, if I use this number, that will change the 5th decimal place because it affects the first 3. Those for sure are going to have an effect. So I figure out what 1 over 7 times 8 factorial is, and that turns out to be 0.12345 3543. So now I know that this is 1, 2, 3, 4, 5. And if I figure out what this is, that is negative 0.486388889. Now, if I am to look at the decimals, 1, 2, 3, 4, this says it's going to affect 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If I stop right there, wouldn't that not affect the outcome of these numbers? And that's 5 decimal places, because if I put a 3 there, 5, 4, 3, subtracting that will keep that a 5. So this would still be rounded to 9. And that would be my answer. And that's pretty much it for this section. Now, you're going to have to get a scientific calculator, and you need to make sure you know how to use it. And here, even though it might not look as important, you need to learn this and make sure you figure out why is that changing or not changing.